Welcome back to Differential Equations. In this lecture, we're going to introduce a type of differential equation called a separable equation. And for our course, it turns out to be one of the simpler types of differential equations that we can solve. All right, so what I want to do right now is introduce a type of mathematical problem for our course, something called a first order initial value problem. So we'll use this abbreviation IVP for initial value problem throughout the course. And this is pretty much what our first few lectures will focus on. A lot of the content on exam 1 deals with first order initial value problems. And this problem contains two pieces of information. There's on the left a first order ODE, so a first order differential equation. And then the other piece of information, what we call an initial condition, it's basically a point in x comma y that your solution or function will pass through. Think back to your Calc 1 and Calc 2 courses. Whenever you had like an antiderivative and you had a plus c, maybe you had information, a function value that allows you to solve for the value of plus c. That's what the initial condition will allow us to do to solve for the integration constant that we get. All right, so these two pieces together give us what's called an initial value problem. Now, this is for many of you going to be your transition to maybe some upper level math courses, or maybe it is your last mathematics course. If you do progress into some higher level courses, there's two kind of very important questions that are often brought up in mathematics. For any problem, the first question is, does that problem have a solution? Or in other words, does a solution exist to that problem? All right, and if a solution does exist, is it unique? And that's the term in mathematics that we use to refer to maybe a solution being the only solution. Okay, and these are going to be two questions that we're going to consider for an initial value problem. Does a solution to the initial value problem exist? And if it does, is it unique? All right, now these start to get into some higher level mathematics, and we should be progressing linearly before we start to learn how to solve differential equations. We probably would like to know if there even is a solution to be found. We're going to come back to these details later in this lecture. I would rather focus on some actual examples that we can solve to see how your previous knowledge ties into our course. And once we get through a few examples, we'll come back to this idea of existence of a solution and uniqueness of a solution with a theorem that tells us something about that. All right, so to get started with initial value problems, just think of that as a different type of differential equation with an initial condition. There's certain ones that are very easy to solve. Now think back to our introductory lecture. We mentioned something about antiderivatives, and a very simple initial value problem has a derivative on the left side, but the right-hand side is only a function of x. In other words, on the right-hand side, there are no terms involving y, the function. Now, if that's the case, if the right-hand side only contains x, or is only a function of x, then this is basically just asking us to find an antiderivative. We can undo or cancel the derivative of y. How do you undo a derivative? Integrate. So if you just integrate both sides, integrating will cancel the derivative, giving you y on the left, and we just have to integrate the function f of x on the right side. So conceptually, this type of differential equation, very simple to solve. Now maybe the integration on the right-hand side, integrating or finding an antiderivative for f of x, that could be complicated. Maybe it's simple, but it might be complicated, but theoretically, we just have to integrate. So this type of differential equation, we basically know how to solve. Most of your Calc 2 integration methods would work for these. All right, what we're going to introduce in this lecture is a new type. It's very similar to the statement above about antiderivatives, but it's a very special combination of the right-hand side. So for what we're going to call and define as a separable equation, we have a derivative on the left side, and the right-hand side is a very specific combination of x and y. The right-hand side is a function of x, g of x, divided by a function of y, h of y. Now the name separable equation kind of gives you some idea of what we might try to do. We have to keep in mind that the notation dy over dx, it is not a fraction. It looks like one, but recall a derivative, dy over dx, is really a limit. If you want to be technical, you can say a derivative is a limit of a fraction, the difference quotient. But we're just going to keep in mind that dy over dx, while it looks like a fraction, it isn't. But for this lecture, we're going to pretend that it is. So we're going to separate that derivative into individual differentials, dy and dx. And that's where the name separable comes from. Now, what does that do for us, splitting up the derivative into individual differentials? Well, take a look at the form we gave right above for a separable equation. And if you think of all the quantities in there are parts of fractions, we're going to cross multiply. So we'll multiply both sides by h of y, and we'll multiply both sides by dx. If we do this, we get this particularly nice form for this separable equation, where we have individual kind of functions multiplied by an appropriate differential. So on the right side, we have a function of x times dx, and on the left side, we have a function of y times dy. Now, if you can write your differential equation this way, we would say it's been separated. So just make sure you understand the notation. On the left side, it's a function of y times dy. There can't be any addition or subtraction between the function of y and the differential dy. And on the right side, it's a function of x times dx. If your differential equation can be written this way, it's separated. All right, so what does this actually do for us? Take a look at what we have at the top of the screen for the first type of example. The notation looks very similar. So we have kind of two different differentials, dy on the left, dx on the right side. Basically, we're going to integrate both sides. And this gives us the same sort of idea as the first type. We just have to integrate now both sides. As it turns out, the integration could, as always, be difficult to carry out. All right, so unlike the first example, which only requires integrating once, here to kind of undo the derivative appropriately, we separate into individual differentials and then integrate both sides. All right, let's take a look at some examples. I'd like to go through with one with you together that's rather simple. So we're going to work through example 1 together, where we're going to solve the differential equation dy over dx equals y. And we have an initial condition given to us, y at 0 equals 3. So the notation here, because we're thinking of y as a function of x, that's saying when x is 0, the y value is 3. All right, so let's start by trying to separate the differential equation. If you think back to our introductory lecture, we did look at this example where we thought of trying to find a function, y, that is its own derivative. And that's what we mentioned should be an exponential function. So when we go through the process of separating and then solving the differential equation, we better get, at the end, some sort of exponential function. All right, this one, pretty simple to separate. we can multiply the dx to both sides, but then divide the y over. At this point, it's separated. We have 1 over y times dy, and then equals dx. All right, at this point, once it's been separated, we can integrate both sides. All right, we're integrating the left side with respect to y, and we integrate the right side with respect to x. All right, so at this point in the course where it's good to kind of just to keep on top of your basic antiderivatives, most of the examples so far aren't going to be too bad, but in the next example and beyond, we'll kind of throw in some other integration methods. Here, this should be pretty straightforward. All right, if you integrate 1 over y dy, that should integrate to natural log of y. And then integrating dx, just gives you just x. Always check by going backwards by differentiating. Dx on that right side, that integral, it really can be thought of as 1 dx. And if you differentiate x, you do get 1, so that checks out. All right, now a question that usually arises in class when I go through this example, which I want to bring up to you now, is we don't need 2 different integration constants. So we're integrating the left and right sides, but we only need a single integration constant. I'm always going to include that on the right side, the integration with respect to x side, just for consistency. Let's take a look at what happens if we included 2 integration constants. It's not wrong to do that, but let's see. So let's say we integrated the left side and we got natural log of y plus a constant d. The right side is still x plus c. All right, now if we treat both c and d as constants, just numbers, you can subtract d to the other side, and c is a constant, d is a constant minus a constant is some other constant. So this really is the same as what we did for the first time, just including a single integration constant on the right side. Including 2 is just a little redundant. All right, so with that, we have what we're going to call the implicit solution. So we basically have solved, we undid the derivatives. For an implicit solution, this is where the solution that we get is not solved for y. Think back to Calc 1 with implicit differentiation. All right, now this in this form does not look like what we expect above at the top. We expect to get an exponential function for our solution. This is one of the examples where we actually can, for minimal effort, convert our implicit solution to what we're going to call an explicit solution. Here, we can pretty easily solve for y. So let's go ahead and do that. So first, if we're trying to solve for y, we would want to undo or cancel the natural log. So we would exponentiate base e for both sides. All right, just to kind of introduce another idea with constants that we're going to continue to see. Notice on the right side, e raised to the x plus c, using some basic exponent rules, we can rewrite this with multiplication. So instead of adding in the exponent, we can multiply the bases. Just make sure you're comfortable with that. We're using this exponent rule kind of in reverse from what you might be used to. So just check e to the x times e to the c, same base, so you can add the exponents to get e to the x plus c. All right, now the point for this is that there's a few different ways we can include the constant. Since we use exponent rules to rewrite this to contain e raised to the c, e is a constant, c is a constant. What's a constant raised to a constant? Another constant. So we can rewrite this right-hand side there as e to the x times a constant c. Might be better to rename it, but we'll usually use c as the constant. All right, make sure you're comfortable with this. We're just basically rewriting it using exponent rules and then getting rid of any unnecessary or complicated looking constants. All right, so we get our explicit solution here, y equals c times e to the x. And what we call an explicit solution, it's one where we have solved it for y. And notice that matches our expectation. We do now have an exponential function for y, which we expected from the beginning. All right, the only other thing we need to do to complete this problem is to use the initial condition. And that's just a matter of plugging in an x and y value and then solving for c. So make sure you're comfortable with the notation here. That is not y times 0, but y as a function of x, where we're plugging in x as 0. It's a kind of hybrid function notation, reminding you that y is a function of x. So if we go over to the explicit solution, we're going to plug in x as 0 and simultaneously y as 3. That should give you a way to then solve for c. All right, and this is pretty simple. I don't have a calculator anywhere, but oh, e to the 0, I know that's 1. So what we find here is we get c comes out to 3. So we have our complete solution. So a function that satisfies the differential equation as well as satisfying the initial condition. So that explicit solution is y equals 3 times e to the x. All right, now this was a very simple one to go through together, but it gives you an idea of how we separate, how we use the initial condition, and introduces implicit and explicit solutions, as well as some peculiar algebra involving the constants involved. All right, when you're ready, we'll move on to example 2, which I'll give you an attempt at. All right, if you're ready, let's take a look at example 2. All right, this one I'd like you to try, so pause the lecture, give yourself a few minutes. This is something that in class I would give to the entire class to work on. So pause, and we'll check in a few minutes. All right, welcome back. Hopefully you got through this one pretty effortlessly. We'll go through most of the steps together here now that you made an attempt at it. At any point, if you maybe got stuck and then some of the work that we have on the screen together here gets you unstuck, maybe repause and see if you can complete the problem from there. Okay, so this one we're going to separate. Notice we have combinations of x and y. What we can do is basically multiply and divide, basically flip that fraction, y divided by 1 plus 2y squared. We're going to flip that to the other side. So basically we'll divide by y and multiply both sides by 1 plus 2y squared. With that, we're going to also multiply both sides by dx. All right, if you do that, we get to here. This differential equation has now been separated. Now, to make the integration for both sides go as simple as possible, notice you can rewrite the fraction on the left side. You can divide y into each term in the numerator. That's since we're adding in the numerator. So we can rewrite that left side, or the integral on the left side, as the integral of 1 divided by y plus 2y. There's a factor of y that cancels out there. Y squared divided by y. All right, at this point, the integration should be pretty simple. The left side will integrate to natural log of y plus y squared. And then integrating the right side, basic antiderivatives for trig functions. An antiderivative for cosine is sine of x. And then, of course, plus c. All right, so at this point, we have an implicit solution. And due to the combinations of y on the left side, this is actually going to be very difficult, if not impossible, to solve for y. There's not going to be any way we can undo y squared and natural log of y at the same time. So we're not going to bother with getting an explicit solution, trying to solve this for y, since it's, for this one, I think it's actually impossible. We can still solve for c, though, the integration constant. The initial condition has the x-coordinate as 0 and the y-coordinate as 1. So if you take your implicit solution there and plug in all y's with the value 1 and all x values with 0, you should get to here. And there's some nice values here, both natural log of 1 and sine of 0 both equal 0. So we should find the value for our integration constant comes out to be c equals 1. All right, so we just plug that back in to the implicit solution above, and we get our implicit solution, which is completely fine. Most of the examples we'll be looking at, most of them are actually probably not worth trying to solve for y, since they might be either very difficult or impossible to get y by itself. We'll mention, where appropriate, which ones you would want to give an attempt at. All right, so for example 2, that's it. We're going to take a look at a third example, which again, I'll give you an attempt at. Let's think the examples so far, the integrations haven't been too bad. So you might be getting the sense for, yeah, my integration skills are pretty good. Let's see how good they are with example 3. Now, example 3, before we advance to the next slide, the integration should be kind of doable just from, a solid understanding of Calc 2. All right, so when you're ready, let's take a look at example 3, where the integration might get a little more complicated. All right, so I'd like to give you an attempt at this. I would expect for many of you, you might have some difficulties with kind of both the integrations with respect to y and x once you separated. That is to be expected. We're really just getting started with our course. So reach out to me if you find that your integration skills aren't where you'd like them to be. We'll mention after the example here what integration methods you should be completely proficient with to do well in our course from the beginning. So I want to give you an attempt. Pause the video and give yourself several minutes to attempt this. We'll check in a few minutes. All right, welcome back. Now, hopefully you correctly integrated the examples here, the integral that appears on both the left and right sides. There's some common mistakes which we'll point out, so let's see. This one's pretty easy to separate. We can divide y squared minus 1 to the left side, and we can multiply dx to the right side. All right, so at this point, it's properly separated. Certainly fine to have fractions, but make sure they are fractions that contain the right variables. Notice on the left side, we have a fraction involving y times dy, which is what we want. And on the right side, we have a fraction containing x multiplying dx, which is again also what we want. So this is properly separated. All right, at this point, once it's separated, we just have to integrate both sides. Sounds really simple, right? Well, as it turns out, there's a good amount of work. There's some work to be done with the left side that we can do with a partial fraction decomposition. The right side, or the integral on the right side, that comes out to be an inverse tangent, which might be a formula you might be familiar with, which we'll review momentarily. All right, now I realize coming in, maybe Calc 2, kind of our prerequisite for the course, might have been a while ago. So your integration skills might be a little rusty. That's okay. That's a great thing to follow up with me during my virtual office hours for. All right, so let's put the problem here on hold. We'll go through integrating both sides individually. Let's start with the integral on the left side, where we'll carry out the partial fraction decomposition. All right, now I have all the work here, so I'm going to assume that you're pretty proficient with partial fraction decomposition. This is the simplest of all 4 cases for a partial fraction decomposition. All right, so we're going to start by taking that fraction, factoring the denominator. Factors as y plus 1 times y minus 1, and the partial fractions, each numerator gets a constant. So our partial fraction decomposition, we get a divided by y plus 1 plus b divided by y minus 1. All right, if you clear fractions, multiply both sides by the LCD, you'll end up eliminating fractions completely. And what we can do is plug in appropriate values for the variable, which is y here, that will cancel out some of the terms. So the 2 values that we would ideally like to plug in are y equals 1 and y equals -1. And if you plug those in, you should find b comes out to have the value 1/2, and a comes out to have the value -1/2. All right, if we go back to our original integral, we've completed the partial fraction decomposition, and now we can integrate those individual partial fractions, both of which integrate to natural logs. All right, so again, make sure you're comfortable with this. Maybe this was enough to kind of bring back some long forgotten details of partial fraction decomposition. Maybe you feel like you need more time reviewing that. So again, great thing to follow up with me during my virtual office hours. All right, so that's the integration on the left side. Let's take a look at the integration for the right side, which we said comes out to be an inverse tangent of some sort. Now there's really not a lot of work to it. We're going to start by reviewing a basic antiderivative, the antiderivative of 1 divided by x squared plus 1. Now, this was learned in Calc 1, but that was maybe so long ago, maybe you've forgotten your derivatives of inverse trig functions. We basically flip that around to get now this antiderivative statement. The antiderivative of 1 divided by x squared plus 1, that antiderivative is inverse tangent of x plus c. All right, now our denominator, it doesn't have x squared plus 1, but x squared plus 4. You can do this with a substitution, but we're just going to kind of state this as a useful formula, which ideally I'd like you to memorize. If we have an integral of 1 divided by x squared plus a squared, where a is a number, the antiderivative is an inverse tangent but it's a little more complicated. It comes out to be 1 over a times inverse tangent of x divided by a plus c. Now this is a really nice simple formula which we'll be seeing throughout the course, and it just basically requires us to identify the value of a and then plug it in. So there's no real work here, but you kind of have to know this formula, which is a great formula to know for those of you continuing into some other science and engineering courses. All right, so if we take a look at our integral here, was the integral on the right-hand side of the equation that was separated. We have x squared plus 4. We're going to think of 4 as 2 squared. So for this integration formula, we're going to use the value of a as 2. So just plug it in, and we get our antiderivative for minimal work or minimal effort. All right, now maybe these two integrations caught you off guard, but better to get that out of the way from the beginning rather than have that to keep occurring throughout the course. All right, if needed, go back and review, rewind if you need, pause, just to make sure you kind of thoroughly understand both integrations. We're going to proceed with putting this together to complete example 3. All right, so the work from the previous 2 pages, we just put the integration here, and at this point, we're done. For example 3, there was no initial condition, so we don't have any information to solve for the value of plus c, so we can just leave our solution as is. This one, we can just leave it as this. This is our implicit solution, which is totally fine for this example. All right. Now, before we get to the last part, addressing the existence and uniqueness theorem, this is probably a good time to mention what integration methods from Calc 2 that you need to be completely proficient with to kind of do well in our course. Unfortunately, it's not all of the integration methods from Calc 2, but there's 3: substitution, integration by parts, and partial fraction decomposition. If you feel completely proficient with these 3 integration methods, or in other words, if you got through example 3 pretty easily, you're in great shape for the course. If any of those integration methods are a little shaky for you, don't worry, you can still do well, but we're going to, for the next few lectures, come up with a lot of integrals which involve these 3 methods. So reach out to me during my virtual office hours, and we'll kind of review those integration methods that you need. All right, when you're ready, let's take a look at the last part for this lecture, a theorem that addresses the existence and uniqueness of a solution for an initial value problem. All right, so I like to motivate mathematical theorems with a concrete example. So let's consider this one here. The derivative of y with respect to x equals y times e raised to the xy with the initial condition y at 0 equals 0. All right, unfortunately, this one is not separable. So with our really one integration method for differential equations, an equation being separable, with that not being able to be used here, we're kind of stuck. Now, keep in mind, for an initial value problem, we're looking for a function that solves the differential equation as well as satisfying the initial condition. Now, if needed, pause and try to think of a very, very deceptively simple function, y equals something, that satisfies both the differential equation and the initial condition. We'll check in a few seconds. All right, any ideas? Well, one solution, which again is deceptively simple, is just y equals 0, which sometimes is referred to in mathematics as the trivial solution. Notice satisfying the initial condition doesn't matter what you plug in for x to that function. The output value is always 0. This is a constant function. And notice y equals 0 also satisfies the differential equation. Just think, what's the derivative of any number? What's the derivative of 0? 0. So plug it into the differential equation. The left side becomes 0. The factor of y out front makes the right side 0. So it works. Y equals 0 satisfies the differential equation and the initial condition. Now, this probably seems too simple. You might be thinking, are there other solutions out there that maybe requires another method? Maybe this, since this isn't separable, we can just use another method. But is there another solution? This is where our theorem comes in. And it's known as the Picard-Lindelof theorem. And it addresses the existence of a unique solution to a first-order initial value problem. So for this theorem to apply, we're trying to solve a first-order initial value problem. So we have the differential equation and initial condition. And the conditions that the function and differential equation have to satisfy are that if the function and its first-order partial derivative with respect to y, if both of those are continuous on some region containing the initial condition, then there exists a unique solution. All right, now this starts to get into the territory of multivariable calculus. We're not going to go into much more detail. I'll just say almost every example of a differential equation that you would encounter within your science and engineering courses satisfies these conditions. So in other words, if you get a first-order initial value problem within your science and engineering courses, the Picard-Lindelof theorem would say that there exists a unique solution. All right, now for our example above, we have one solution, and the Picard-Lindelof theorem would say, well, that is the only solution. So no matter how hard you try, there are no other solutions besides the trivial solution to that initial value problem at the top there. All right, now this is, again, just kind of getting into some more technical aspects. As we continue learning other methods to solve differential equations, this theorem will still apply. So basically, if we find one solution, for the most part, it's the only solution. If you get into some higher level mathematics courses, you might start to see some parts and conditions where the theorem doesn't apply, but that's best left for later. All right, that's it for this lecture. We introduced our first type of differential equation that we can solve by integrating, what we're calling a separable equation.